Assalamualaikum and a good afternoon to everyone. All right, so we'll be continuing on our lessons in chapter 6 with the title The Ideal Gas Law. All right, so the volume of a gas depends very much on the pressure as well as on the temperature. Okay, so when the pressure changes, the volume of the gas also changes. When the temperature changes, the volume of the gas changes as well. Okay, next, the relationship between the volume, pressure, temperature, and mass of a gas is called an equation of state. And the ideal gas law is an accurate description of the behavior of a real gas as long as the pressure is not too high and as long as the temperature is far from the boiling point. So what does this mean? All right, so what we are trying to do with the ideal gas law, okay, is that we are trying to combine the three previous laws that you've learned, okay, Boyle's law, Charles' law, and Gay-Lussac's law, into one singular equation that you can use when the situation is right, which is the pressure is not too high and the temperature is far from the boiling point. Okay, and here we see that the temperature, the equation for the ideal gas law is as given. Okay, so what you might notice is that it has some of the parameters that was used in your Charles' law, Boyle's law, and Gay-Lussac's law. Okay, so if you remember, we have PV is equal to a constant, and then we have V over T is equal to a constant, and we have P over T is equal to a constant. Okay, so these are your three equations that you've learned before. Okay, and what we are trying to do here again is we're trying to combine all three of these equations into one single equation to make it easier, okay, in a particular situation. Okay, so what was the particular situation as was said in the previous slide. Okay, so here what we can get, here is that PV is directly proportional to temperature. When you multiply pressure and volume, the number that you get is directly proportional to the temperature, right? And then by just manipulating the equation, you will get PV over T is equal to a constant. Okay, right? And as was given by the previous three laws, okay, when it is equal to a constant, you can get, or you can summarize this equation into the last equation given. Okay, P1 multiplied by V1 divided by T1. Okay, so what does that mean? It's just that P multiplied by V divided by T at one particular situation is equal to P multiplied by V divided by T in another situation. Okay, so just remember that for situation 1, PV over T is equal to situation 2, PV over T. Okay. Right, next, let's look at this example. Okay, in this example, what we are trying to do is just that we are trying to show you the relationship between volume and mass. Okay, so imagine you're trying to blow a balloon. Okay, you're trying to blow a balloon up, and when you think about it, okay, as you are trying to blow your balloon, most probably the temperature around you and the pressure around you is constant. You don't feel that when you're blowing the balloon, the temperature changes from, let's say, 30 degrees to 0 degrees. It doesn't happen. Okay, as well as pressure, it doesn't happen. It stays constant. So what will happen is just when you blow air inside the balloon, inside an enclosed system, okay, the volume increases inside the balloon because of the increased mass that you are putting inside the balloon. Okay, so here we get the next equation. Okay, volume is directly proportional to mass. When mass increases, volume increases as well. And because from the previous equation, okay, the previous equation we got PV is directly proportional to T. Okay, and we can just add, okay, we can just multiply M with the T because it's constant, okay? That to the right side in this situation, just for simplification's sake, okay, M you can just multiply inside the equation because it's multiplied by a constant. Okay, so you get PV is directly proportional to M multiplied by T. Right, next, let's look at a mole. Okay, so I believe you've learned about the mole in chemistry, and here there's no difference. Okay, a mole is a number. Okay, it's just a number, and for how you want to get a mole, okay, you will follow this equation. So N, okay, the symbol for a mole, is equal to the mass in grams divided by the molecular mass in grams per mole. Right? So if you look at this, it's basically the same as you've learned in chemistry. Okay, so most of the time, students will still have difficulty in remembering what is a mole. Okay, right. By definition, a mole is just a set of numbers. Okay, a collective of numbers. So, for example, when I tell you that I have a dozen eggs. Okay, I have a dozen eggs. What does that mean? It means I have 12 eggs. Even though I never said the number 12, I just said a dozen. Okay, but you understood that a dozen is equal to 12. Okay, so it's the same thing here. A mole is just a group of anything that is multiplied by Avogadro's number. Okay, so the mole is very related to Avogadro's number. Every time you say anything n moles, okay, that means that that particular thing has n multiplied by the Avogadro's number, which is 6.022 times 10 to the power of 23. Okay, so for example, as given below, okay, 1 mole of H2 has a mass of 2 grams. Okay, 1 mole of Me has a mass of 20 grams. 1 mole of CO2 has a mass of 44 grams. And given the equation. Okay, so again, a mole is how many numbers multiplied by Avogadro's number. But here, because you're given the equation that the mole is also related to the mass and the molecular mass, you can find out, if you wanted to, the mass as well as the molecular mass if the appropriate number is given. Okay, so here, even though they didn't give you the molecular mass for H2, for Ne, for CO2, you can simply find them in your periodic table. Okay. All right. Next. All right. So again, from the ideal gas law, we have PV is directly proportional to mass times by temperature, and you can also make this equation. Oh, sorry. Okay, you can have this equation, PV is equal to nRT. So if you just look at the parameters that's there, PV is, okay, PV is here, and T is there. So only NR is new here, right? So what is NR? N is the number of moles, and R is the gas constant given below. All right? So why can we add the N and the R suddenly inside this equation? Okay, because one, it's a constant. Okay, you have your R is the gas constant and N is just a number. Okay, N and R both are constants. All right. Okay, next, the ideal gas law always refers to standard conditions or standard temperature and pressure. Okay, so if you remember, The ideal gas law, you can use it when the pressure is not too high and the temperature is far from boiling point. And here we get more specific. You can only use it when it is in standard temperature and pressure. So what is the standard temperature pressure? Temperature is 273 Kelvin or 0 degrees Celsius. And pressure is 1 atmospheric pressure or 1.013 times 10 to the power of 5 newtons per meter squared or 101.3 kilopascal. Okay. And then given also the note, okay, 1 mole STP gas has a volume of 22.4 liters. Right? And then next, let's look at this exercise. Okay, determine the number of 1 mole of a gas assuming it behaves like an ideal gas at STP and an automobile tire is filled to a gauge pressure of 200 kilopascal at 10 degrees Celsius. After a drive of 100 kilometers, the temperature within the tires rises to 40 degrees Celsius. What is the absolute pressure within the tire now? Okay, try to do these 2 examples, okay, these 2 exercises, and submit to your respective lecturers to discuss it further. All right, so again, let's look at Avogadro's number. So why is Avogadro's number important in the ideal gas law? Because you have the mole there. Okay, you have N, sorry. Mole is inside your ideal gas law, so it is inevitable you will be using Avogadro's number. Okay, so let's look at what is written here. Since the gas constant is universal, the number of molecules in 1 mole is the same for all gases. That number is called Avogadro's number, given below. And then the number of molecules in a gas is the number of moles times Avogadro's number. Okay, so previously I stated that Avogadro's number is 6.022 times 10 to the power of 23. Here it is written as 6.02 times 10 to the power of 23. Okay, use which is given in your questions. So if for a standard question, you will be using this number. Okay, and then the relationship between the number of molecules and the Avogadro's number is given as the bottom equation, right? Okay, and this is just expanding on the ideal gas law. Okay, PV is equal to nRT is equal to N over NA. Okay, multiplied by RT, and we have this new equation. So where did this new equation come from? Okay, this new equation is just RK, the K here is just R divided by N over A. Okay, where K is the Boltzmann constant, or 1.38 times 10 to the power of negative 23. Okay, here is just a manipulation of equation. Okay, nothing much here. And last for this subtopic is this exercise. Try to do this equation, this exercise, and submit to your respective lecturers. Okay, with that, this is the end of ideal gas law. Okay, thank you very much.